in fact, the aim of this particular lecture is to explain, or try to explain, how I think that the slopes à la Bost, as they were described, for example, in the lectures of Eric Gaudron, might be quite a central tool to study the distribution of rational points of bounded height on almost fado varieties. So I must admit that, in fact, one of the reasons for which I co-organized this school was to learn more about Arakelov geometry, so I was to be able to better use it. So in some sense, it's quite possible that when you see what naive way I have to use the slopes à la Bost, you will tell me that, well, there is a much better way which would be much better to do that. So anyway, so let me first explain the problem I have. So the beginning of the talk will be again to speak of height. So once more, height. So again, I'm going to define them. So it is about the third or fourth definition of heights in this summer school. So the point is that each of us have a favorite way to define heights. And of course, all of them are connected, and maybe the generality is slightly different. For example, since I'm interested in rational points, I will be very lazy about extensions. So everything will be over ground field. So there won't be the nice things, subtle things about, for example, the topology, which was defined by Eric Gaudron in his talks and things like that. So I'm going to stay over ground field. But on the other hand, I want to do it not only over a point, but over a variety. So I'm going to explain all that. So at least to fix the notation, I'm going to explain again about height. OK, so the first part is about heights and distributions. So the first thing I have to explain is the concept of adelic metric. So it will be, the terminology is slightly different from the one I think which was used before. So in fact, the heights I'm going to use will be defined by adelic metrics. So for me, in some sense, adelic, OK, so the point of view of Arakelov geometry, in some sense, is that you have, for example, a model over a ring of integers, and then you add extra data at the infinite place, so you got this nice thing which is over all possible places number field. What I'm going to do is, in fact, for me, an adelic metric is like a Riemannian metric, which is classical in differential geometry, but you do it over all places. So in some sense, I'm going somewhat in the other direction. I start with a concept over the infinite place, and I use it in some sense over all places. But in some sense, Arakelov geometry says exactly that you can somehow do the same over all places. So this is what I'm going to do. So K is a number field. Well, I should have changed my notations, but since I wrote my notes, I decided to keep them. Also, they are not the same as before. So val of K will be the set of places of K. And also, well, for any W in the set of places of K. So as usual, KW is a completion of K. And then I'm going to do something which is really bad. So if V is the restriction of W to Q, I'm going to define or to normalize the norm on KW going to R by putting that X of W is defined as the absolute value of the norm from KW to QV of X. So this is not the convention which was used before. So I mean, there is this is the one which was used before, but at the power KW over the degree of KW over QV. So why I am using this notation? The main reason is that because I'm lazy. See, because I don't want to write each time the degree of the extension. So this is the main reason. So of course, I could fix a notation for the degree and then use it, but okay. The other reason, which is maybe more acceptable, is that, in fact, if you look at the R measure on KW, so KW is locally compact, so it has a R measure, which is invariant under translation. And I can normalize it. Well, I have to normalize it in some way. So, for example, I can normalize it by saying that the volume, the volume of the ring of integer is equal to 1 if W is non-Archimedean. D of XW is equal to the usual Lebesgue measure if KW is isomorphic to R, and dXW will be twice dx dy if KW, well, which can be described as dz bar as well, but okay. So if KW is isomorphic to C. All right, so the point, the relation with this norm is that, in fact, we get the basic change of variables formula, which says that, in fact, this is a multiplier for the R measure. All right. And also, with this convention, we get that the product formula may be written as follows. So the product formula may be written as the product over all places of K of X is equal to 1 for any non-zero X in K. Right. Okay, so then I'm going to define metrics on varieties. So I'm going to consider only nice varieties. The point is that, so what is a nice variety? So it will be a smooth projective and geometrically integral variety. The point is that I do not need to consider a singular variety because, in fact, for the problem I'm considering, more or less can reduce to smooth one by using desingularization, at least theoretically. Well, in general, it's not that easy to find the desingularization, but in a completely explicit way. Okay, right, then when I have that, well, I shall consider vector bundles over V. So let I forgot to say, yeah, over K, so over the number field. So I consider a vector bundle over V. So for me, vector bundle is really that, a vector bundle that is, I look at it as a space which locally is isomorphic to U times a vector space. So I am not looking at the locally free sheaves, for example. So be a vector bundle over V. Right. Then, so I should say a classical, but I will forget about that quite quickly. Adelic norm on E is the following data. So it is a family norm at W for W in the set of places of K of continuous functions. So I do not assume any smoothness or things like that. So this function goes from the KW points of E to R, such that so I hope I won't forget any hypothesis. So first of all, if W is non-Archimedean, so if W is ultrametric, then for any x in V of KW, the restriction of the norm to the fiber to E of x, so this is the fiber at x, this is an ultrametric norm. With values in yes, exactly, thank you, with values in the image of the absolute value at W. So this more or less says that it is defined by some OW lattice in E of x. So more or less it says that the set of y in E of x such that the number of y at W is less or equal to 1 is an OW lattice in E of x. Well, on the, it is precisely defined by this lattice. Right, and okay, if W is real, any questions? No. So if KW, well, if W is real, so this means that KW is isomorphic to R, then I assume that, in fact, the restriction to E of x is, well, sorry, I should write here x for all cases. So the restriction is Euclidean. So it is defined by positive definite form, quadratic form on E of x. All right. On the third case, if W is complex, then the norm the norm is given by a Hermitian form. Right. So on the last condition, okay, so now everything is independent over all places. So of course, this gives too much freedom. So there is a last condition which says that for almost all places, this norm is given by a model of E on V. So there exists S finite set of places such that there exists a model E over V of E over V over OS. So I'm considering the ring of S integer. So the point of that is, in that way, I don't have problems with the places of bad reduction. I can put all places of bad reduction into S, and therefore I can choose a model which is as nice as I want, in some sense. Okay, so that for any. So this was defined. I think it was it? I don't remember which lecture. So anyway, so it means that when you tensorize by the number field, you get E on V on the morphism pile. Okay. So for any W not in S, the norm is defined by E. Which says that, in fact, if I look at the fiber E of x, this is precisely for any x in V of Kw, E of x will be precisely the set of y in E of x such that the norm of y is less than 1. Okay, so that's it. So this is more or less which was already in the talks before, in Jean-Benoît Bost's talks, for example. So there is a point. Since I'm considering only a fixed field, I'm not choosing something over here. I'm not going to extension and things like that. So I mean, everything is on the ground field. Right, now that I have defined that, so an adelic norm. So what is an adelic metric on V? Well, I define an adelic metric on V as an adelic norm on the tangent bundle. So as I said, the point is that it's really like Riemannian geometry. Riemannian geometry is that you have metrics, Euclidean metrics on T of V. So we do the same, but for all places, in the sense of Archimedes geometry. All right? Okay, so the question now, what can we do with that? So the constructions which were explained by Eric in his lectures generalize to that setting. So in particular, you can do direct sums. So if you have, by this, sorry, I mean that if you have two bundles with adelic norms, and you can consider the direct sum, you can consider tensor product. So I consider the second construction of the tensor product, so the direct construction where the orthonormal basis is EI tensorized by Fj. Okay. And what can we do? We can do exterior product. We can do lambda k of E as well. So again, it is exactly as in the lectures by Eric Gaudron. So if E1 En is an orthonormal basis of E at x, then the base is given by EI1 exterior EIK for 1 less or equal to I1 strictly less than I2 and so on strictly less than IK less or equal to n is an orthonormal basis of lambda k of E of x. Okay, so as we explained last week, I mean this choice, I mean you have to do the right choice for the exterior product, but this one is working. Right, and of course I forgot, but there is also the dual vector bundle, for which you can do as Eric did in his talk. Okay, so you have all the standard construction which work in that settings without any trouble. So in particular, if you have an adelic metric on V, well, this gives, well, an adelic norm on the opposite of the canonical line model, so which is the determinant of T of V, that is lambda n of T of V, where n is the dimension of V. And therefore, an adelic metric on V gives a height on V which is related to omega V minus 1 relative to the vector model omega V minus 1. I will go back to that in 1 second. Okay, so this was the first sequence of examples. Another very basic but very useful example is, of course, pullbacks. So if you have a morphism of nice variety from x to y, over k. And if you have a vector bundle of y, then you can pull back everything to x, and you get a vector bundle on x with an adelic norm. All right, so let's do the connection with what we have already seen in more details for vector spaces over number fields. So in particular, if V is a point, then we do not get anything new. We get that a vector bundle over V is exactly a vector space. And we can consider, so of course this vector space comes with, with an, with a adelic norm. And we can consider, for example, the set of y in E such that for any ultrametric W, the norm of y at W is less than 1. So this is quite clearly an OK module. But in fact, it is a projective OK module of rank the dimension of E. But of course, it can be, there is no reason for it to be free. Right. So an even more particular case is, of course, the case of a vector space of dimension 1. So if the rank of E is equal to 1, then, as we have already seen, but I'm writing it again because I'm using different conventions, so it's just to write it in that setting. If we look at the product over all places of the norm of an element y, well, this is constant. Of course, it is 0 if y is equal to 0, but otherwise is constant for y in E minus 0. Because of the product formula, of course. I mean, if we multiply y by some constant lambda, then by the product formula, it doesn't change the product. And then we get back the degree of E in that case. So in that case, the degree. So I will put hat. So some people do not. So this will be minus the logarithm of this product. Sorry. Right. Of course, we get a morphism of a group. So we can, okay, so I should define, or no, it's not, I'm not the first one to define it, but, well, anyway. So let's consider the first show group with a hat, so hierarchy of show group of the point. So what is this group? So this is the set of isomorphism class of vector bundles of rank 1 over spec of k, equipped with an adelic metric. Adelic norm, sorry, adelic norm. Right, so I did not define what was an isomorphism, but you can guess easily. So, of course, this is a group because I said somewhere that, but I erased it, that you can do tensor products. And therefore, using tensor products, you get a group law on this Peyre group. And you have a morphism, which is a degree, which goes from the Peyre group of the point to R. And of course, there is a kernel. And the kernel is given by the Peyre group of the ring of integers, which is finite. Right, so that's it for dimension 1. And in higher dimension, well, as we have seen, the degree is simply the degree of the determinant of E. So for arbitrary dimension. Right. So I was supposed to talk about height.
Can you explain much more why you have such concept?
No. No, I think that's not the main point of the lecture. So, okay, it's just to give an idea. I mean, the point is that it's not, I mean, it's not injective here. So this was just a remark. I mean, nothing more. Sorry, is there something wrong? Okay, so let's turn back to height. So this was done before. I mean, I'm just reminding you about the way to see the degree, the hierarchy of degree of a vector bundle over a point. So one way to define it is to say that it is the hierarchy of degree of the one-dimensional space determinant of E. Okay, so for for dimension 1, this is given by this formula. And for higher dimension, you take the determinant and you take the degree of the determinant. So the determinant, oh, maybe I should say again that this is lambda R of E, where R is the rank of E. I should have said that. Right. Okay, so now I'm considering a vector bundle E over V equipped with an adelic norm. And I want to define a height which corresponds to this vector bundle. So this is done as follows. This goes from the rational points of V to R. So this is a logarithmic height associated to this data. And which is defined by simply, to a point x, I associate the degree of the pullback, well, of the fiber of E at x. Right. So, in fact, this you can see the E of x is simply the pullback. So x corresponds to a morphism from spec k to V. And A of x is nothing else than the pullback of A by x. And therefore, this is a vector bundle over a point. And you can take the degree. All right, so I'm doing it for arbitrary vector bundles with adelic norms. Well, it doesn't bring, up to now, anything new. I mean, the point is that, of course, so this is probably the first stupid remark I should make, that this HE is H of the determinant of E. So it is a height given by a line bundle. I mean, I'm not, up to now, there is nothing new when compared with heights defined by line bundles. But later on, there will be something more. Well, I realized that nobody gave a trivial example, I think, of that. So let me give a trivial example of such a height. At least only for me, just to reassure myself that I've not mixed up the conventions. I'm always afraid about the sign which I should put in front. Okay, so all right, so let's start with Pn. So Pn is a good example. So, well, I can define norms over kw at the power n plus 1, which, for example, everywhere is given by x naught xn goes to the maximum of the xi. So, okay, in the sense I gave before, this is not sorry. Oops, there is something wrong. Sorry. Okay, so if W is ultrametric, sorry, just want, no, that's fine. Let me do that for any W. So the problem I have, the reason for which I'm hesitating, is that this at the real place is not given by a quadratic form. I mean, it's not classical in the sense I gave before. Right, so, but now let's consider the tautological line bundle on Pn. So for me, the tautological line bundle is O minus 1. Over Pn of k. So if x belongs to Pn of k, the fiber of this line model, in some sense, is the line corresponding to x in k at the power n plus 1. So for x in Pn of kw, the fiber OPn of k minus 1 of x is the line corresponding to x in k of w at the power n plus 1. And therefore, I can consider the restriction of the norm to this particular line. So I equip it with the restriction of the norm W to this line. All right, so the point is that since I restrict myself to something of dimension 1, then it satisfies all the conditions. Because in dimension 1, I mean, all the norms satisfy the condition I gave. All right, so what do I get as a height if I do that? So if I take a point in kw n plus 1, in k n plus 1, I take the corresponding point x with homogeneous coordinates x naught xn in Pn of k. And then the height corresponding to O of minus 1 at x is the product, the logarithm, sorry. So that's the point where I discover that all my conventions are completely wrong. Well, no, that's okay. Minus the logarithm of the product over W belonging to the set of place of k of the norm of, well, x naught xn at W. So if I define the, well, I should have defined it before, the exponential height as the composite of the exponential map on the logarithmic height. then I get that HO minus 1 of x is the product over all places of the norm of x naught xn at w minus 1. Therefore, I get that HO of 1 of x is the product over all places of the maximum for I going from 0 to n of xi at w, which is precisely, well, the most classical example of height you can find in the literature, I guess, over a number field at least. Well, okay, let's do it over Q. So if K is equal to Q, then I can choose a representative for an element in the projective space with integral coordinates, co-prime integral coordinates. So take x naught xn, prime integers, then we get that H1O1 of x. Well, the same formula works, but of course, if I take a finite place, the place at a prime, the fact that the x naught xn are co-prime integers means that the maximum of the absolute values is equal to 1. So the only thing which remains is the maximum for I going from 0 to n of the usual absolute value of the xi. So we get the standard height on Pn. Okay, so I have now. Sorry, you have to speak very loudly because of this noise outside. Okay, so as I tried to explain, if you look at the prime number, the point is that x naught xn are chosen to be co-prime integers. So this means that among x naught xn there is at least one which is not divisible by p. So this means that the maximum of the p-adic absolute value of the xi is equal to 1. Okay, so all these terms disappear. Right. So once I've done that, what do I want to do? Well, I want to study the following set. So notation. So let E be a vector bundle with an adelic norm. In fact, later on it will be most of the time it will be in fact T of V with an adelic norm, the tangent space, tangent bundle. And let W be a subset in the set of rational points. Then I want to study W, the point in W with height less than B, which I denote in that way. So this is a set of x in V of k such that He of x is less than B for, well, I forgot to say that B is a strictly positive real number. And in fact, I want to consider this set asymptotically when b goes to infinity. And I want to understand the distribution of this set. So if you have never seen such a set, so most of you have because I often show such pictures, so I'm sorry for them. But I will try to use my gadget. The problem is that I forgot the connector for my Mac, so I have to use something else, and I'm not sure it will work. But you have to try. That's research. So I'm not doing a break unless I cannot make it work. Yep. So I have a code. Yeah. So let's hope it's working. Yeah, it's working. Wonderful. All right. So this is the projective plane, P2 of Q. So the bond I chose for the height has only one reason to be. It is to make a nice picture. Okay, so do not look a deep meaning in the 40. I should have chosen 42, of course, but I made the wrong choice. Right, so this is the kind of picture you get. So here you see there is the point with homogeneous coordinates 0, 0, 1. And here you get the point with homogeneous coordinates 1, 0, 1. At the top there is a point with coordinates 0, 1, 1, and so on. All right, so that's the first picture. So now I want to go to the next case, which are, let's say, quadrics in P3. So of course, I start with the hyperbolic quadric. So the equation xy is equal to zt. The point is, of course, it is isomorphic, as you know, to P1 times P1. So in fact, it is also the picture for P1 times P1. So, well, OK. Again, you can get a nice picture. So if you think of it as P1 times P1, the horizontal lines and the vertical lines correspond to the fiber to the first and second projection. So you see, I mean, these sets are defined in the same way, I mean, with bounded height, but already you get pictures which do not look the same. OK, so this was the first kind of quadrics, but of course there is another kind of quadric, which is a sphere. So this is a sphere. So the point, OK, that's not totally obvious, but the points are blue. OK, so that's rational points of bounded height on the sphere. So as Daniel Lugram can tell you, this is exactly the picture as the points on P1 over Q of I. So you can see this either as a sphere in P3 or as the points in P1 of Q of I, because the descent of the P1 of Qi is exactly the sphere, Riemann sphere. OK. So what kind of question you can ask about this kind of sets? So a very natural question is that, OK, I take an open and simple open subset for the real topology, and you can ask, well, what is the proportion of points of bounded height which are in this area? Okay. So this is exactly the type of question I want to answer. And this is the meaning for me of distribution. So I'm going to be more precise and more specific, but more or less, the question I'm asking is exactly that. You take some simple subset, and you want to estimate the proportion of points which are in this subset. Okay, the pause is finished. No. Right. I still have half an hour, right? Yes?
So in the picture you just showed, if you use a computer, say, to actually compute the number of points in that thing you drew in the proportion, and then take a limit as the height goes through the thing, you get something all the time?
Yeah, I mean, yeah, you can do that. You can do that. For simple example like PN, it's quite easy, and you can go to a big enough height to have something which makes sense. But if you take more complicated varieties, then the convergence can be slower, and then it's harder to see something on a computer. All right, so let me start by saying a few things about this kind of sets. So first of all, there is no reason in general for this set to be finite. In fact, in general, this set is infinite. I mean, for example, if you use height corresponding to O of -1 on Pn, well, all the points have height which is smaller than some constant. So, I mean, okay, so the first thing is you have to put some restriction on the kind of height you are using. So first easy result, which was already mentioned, is if L is a big line bundle, and you take height relative to L, then there exists some open subset U in V. Oh. So by this I mean that it is a sum, well, its class up to some multiple is a sum of a non-pole line model on an effective line model. Or you could say that it is inside, it is in the interior of the cone of effective line bundles. Where was I? Yeah, I was here. Then there is a dense open subset U in V such that for any B strictly positive, the set U of rational points in U with height less than B is finite. The proof of that is quite simple. Well, I'm going to give only sketch of proofs. I'm not going to give all the details. So the sketch of proof for that is that since L is big, then by choosing some multiple of L, there exists some dense open subset dense open open in V such that the map defined by L power M, so there is a rational map from V to the projective space associated for me to the dual of H naught of V with, well, the section of L at the power M dual. So I'm taking the dual because I consider the projective space to correspond to line and not to hyperplane. So I'm not following Grothendieck, I guess, in that. So this is isomorphic to P some n of k. So this rational map is, well, injective on U, on even an immersion on U. So for that, you find some multiple of L, which can be written as something which is very ample with something effective. And then you remove the base point of the effective bundle, and then you get something like that. All right, so once you have that, you can use the Northcott theorem. So, wait, I should say that then U of k, H less than B, will embed into where am I? Pn of capital N, Pn of k, some 8 relative to O of 1 less than B at the power. No, this is B. Okay, I should be careful. Well, something like. Sorry. So the pullback of O of 1 is L at the power M. Well, something like B 1 over M. All right, and this is finite by Chanuel's theorem or Northcott theorem. Yes?
Your choice of the metric is the one you were saying before, with the master.
Sorry.
As an adelic norm, you choose the one with the maximum that you were saying before. Or do you choose for any adelic norm?
No, this is true for any adelic norm. Yeah, good point. This is precisely what I intended to say right now, so thank you. So there is a proposition which says what is going on when you change the adelic norm. So thank you. It was precisely what I wanted to do now. So the point is that if you choose two adelic norms, it doesn't change too much. So let H and H prime be heights. Well, I'm using capitals for uppercase H for exponential heights. So let H and H prime be heights relative to the same corresponding to different adelic norms on the same line bundle, on the same vector bundle. Then, in fact, the quotient H over H prime is bounded. So more precisely, there exist two constants C and C prime strictly positive, such that for any x in V of k, E is less than h prime of x divided by h of x is less than C prime. So you see the finiteness does not depend on the adelic norm. So the proof of that is quite obvious once you think of it. The point is that you can look at the quotient of the norms. And the quotient of the norms makes sense on the adelic, on the projective bundle associated to E over KW. Because if you have two norms, I mean, the quotient is constant on a line. But of course, these kind of spaces are compact. So there is a minimum and there is a maximum. And moreover, the quotient, by definition, since we decided that for an adelic norm, at almost all places it is given by a model, then this implies that this quotient is in fact constant and equal to 1 at almost all places. By this I mean by at all places except a finite number of them. Right. So let's go back, or let's turn, because I've not started. Okay, this is almost the end. I've not started. Okay, anyway, so it's a good thing that there are several lectures. So let me now turn to the distribution. So I will start with the basic examples, which I've shown in the picture, basic example, which is Pn of k. So of course the point is that if there is something which is not even true for the projective space, you won't go very far. Okay, so let's start with that. And let's try to do something on the projective space. So the picture I've shown to you, well, was to look at, I took an open subset, a simple open subset in the real points. But of course, we are in advanced summer school, so we look at the adelic space associated to the space. So of course, since we are over the projective space, the adelic space associated to the projective space is very simple to describe. It is simply the product over all places of the KW points. Because in fact, the KW points are the same as the OW point for the projective space. Sorry. All right, no, that's the page. Okay, so I take this. And now I take a continuous function. So this is what was described in one of these lectures about the, how is it said in English? The weak convergence of probability measures. Is that the right term? I think. Sorry. So let's take F to be a continuous map on the Delic space with real values. Okay, so what is the question? Well, in some sense, the problem is exactly as when you try to learn integration to students in the second year of university or even first year of university. Namely, you consider Riemann sums. So my Riemann sums are slightly more complicated than in the second year of the university. But okay, you consider the sum for P in Pn of k with height less than b of f of p, and you divide by the cardinal of Pn of k for height less than b. Well, does this quotient, does this have a limit as b goes to infinity? Well, for Pn, the answer is positive. Where is it? So let me state it as a proposition. So as b of f converge to, so as b goes to infinity, to the integral over Pn of ak of f with some measure mu Pn, where mu Pn is quite easy to describe. So mu Pn, first of all, is the product of measures over all places. Let's say mu Pn W, where mu Pn W is a Borel measure on Pn of Kw defined as follows. So if W is non-Archimedean, well, if W is non-Archimedean, it is the most natural measure you can imagine on Pn of Kw. More precisely, let's consider the reduction map. So you can consider the reduction map modulo some power of the maximal ideal. So this goes from Pn of Kw goes to Pn of OW over MW at the power k. So reduction modulo MW at the power k, where MW is the maximal ideal in OW. So this is, of course, a finite set. And then you take the volume of mu W to be, so of pk minus 1 of x, to be equals to the cardinal of x divided by the cardinal of Pn of OW over MW, for any x in Pn of OW over MW at the power k. So the most obvious measure you can imagine on Pn of Kw. Well, if W is Archimedean, then you have to do it slightly differently. So you have a map pi which goes from Kw at the power n plus 1 to Pn of Kw. And mu W of some set U, well, U, okay, will be simply the volume. So some Euclidean volume, it doesn't matter which one, of P minus 1 of U intersected with the ball for the norm W I chose at this particular place of 1. Oh, I forgot to say, yeah, here I'm using, in fact, the norm W I gave before with the maximum. All right? So this one divided by the volume of the ball. So in fact, the ball in that case, since I took the maximum of the coordinates, is a cube. Right. Well, I think that's it. Okay, this is a statement. So I mean, in some sense, it is the most natural thing you can imagine. I mean, okay, it's true. Right. So let me give a short remark. On the picture, I was speaking about what is the proportion of points in this subset. And here I spoke about these sums for continuous functions. So of course, the both are related. More precisely, if I take some subset W in the adelic space, which is, let's say, open in the adelic space, and I have to assume something about it, and such that, so this is to avoid two horrible open subsets. The point is that horrible open subsets exist. Okay, so you have to be careful about that. So I take one such that omega mu Pn of the boundary of W is 0. So the boundary of the open subset is not too big. Right, so if I do that, and generally when you think of an open subset, it satisfies that, unless you have a bigger imagination than most people, then the proposition implies that the proportion of points of Woodend height, so W intersected with Pn of k with height less than b divided by the number of points of height less than b, converge as b goes to infinity to mu Pn of W. So it answers the question I asked, what is the proportion of points in W? Well, the proportion of points in W is precisely the measure of W. All right? Okay, so I planned for sketch of the proof. Do I have the time for the sketch of the proof? Yeah, maybe I can try. So let me do it over Q. For sorry, K equals Q. So I will go fast on that. So the point is that it is enough to prove that formula, this kind of formula, for enough open subset W. Because if I'm able to prove that for enough subset W, then in fact by standard measures technique, I can prove that the measure converges weakly to the measure I want, and that's enough. So I'm going to do that for a very particular W. So what is this very particular W? So I take, let's say, a cube C in Rn, which I see as a subset of Pn of R by fixing hyperplane at infinity. And I choose some x naught in Pn of z over mz. So what I want to estimate is the number of x in the projective space over Q, so that so that the height of x is less than b, x belongs to C, and well, let me write like that: the reduction of x is equal to x naught. Well, it's easy to translate that into a question about integers. So this is 1/2 of the number of y in Zn plus 1, such that the DCD of the coordinates, so y underlined, so this is y naught, y n. The DCD of the yi's is equal to 1. The maximum, well, how did I write it? The maximum, well, okay. The norm of y at infinity is less than b. Y belongs to p minus 1 of C, and what else? And okay, I forgot something. Yeah, and y is equal to lambda times, okay, so there is something wrong. What did I write? Yeah, okay. I'm going too fast, that's the point. There exists lambda in Z over mz star, such that y is congruent to lambda times y naught for modulo m, where pi of y naught is equal to x naught. Y naught belongs to z over mz at the power n plus 1. Okay, so then I have, I want to remove this GCD condition. I want to remove the GCD condition, so for this I do some kind of Möbius inversion. So this will be equal to the sum 1/2, the sum for D strictly positive, the mu of D, and then the number of y in d z at the power n plus 1 minus 0, such that the norm at infinity of y is less than b. Y belongs to the inverse image of the cube. And well, let me take my notes because I'm going too slowly. Okay, so I should take the sum as well, z over mz star of y is congruent to lambda times y naught modulo m. But you see, this more or less is counting some points in something which is a lattice. These points satisfying this condition which is the union, I guess, of two convex bodies in the real space. So up to some error term, I'm not going to, well, I'm going to not to speak too much about the error terms. This is equivalent, well, at least, sorry, I'm going too fast. If I look at that, this is equivalent to the volume of the y in the inverse image of the cube such that the norm of y is less than b, divided by dm at the power n plus 1 if the GCD of d on m is equal to 1. And if I'm not wrong, this will be equal to 0 otherwise. So, of course, there is an error term, and one should be careful about the error terms when you do this kind of estimation. But anyway, if you take the sum of that, you get precisely the result I claimed. So, taking the sum of the main terms, you get the result. And then you work on the error terms. So I'm not giving the details, especially about the error terms. But it's not too difficult in that case. I mean, it's more or less an exercise. Okay, so it's working fun for the projective space. And well, next time I will speak about the generalization if that exists. So the point, so let me summarize the next lecture. So I'm going to explain that there is a very nice generalization. And then I will explain that in fact, this very nice generalization does not work. And then I will explain that we are in a terrible mess. And then I will explain how I hope that slopes will help us to get out of the mess. So that's the plan.